Good afternoon, everyone. So I'm really pleased to have Justin Wainwright from Oracle Data Cloud join us for, I think, what's billing to be a very fun and slightly different session. So you would have noticed the Lego paraphernalia dotted around, and Justin will make sense of that in a minute. But yeah, so Justin's a systems analyst at Oracle Data Cloud. He works with around 100 analysts and developers. Hundreds and hundreds of developers and analysts at Oracle Data Cloud that use Qubole. So he's, over the past 3 years, he's been driving that consumption of Qubole at Oracle Data Cloud, and I think we're going to find out a bit more about that now. So welcome, Justin.
Okay, as he said, this is going to be a little bit more of an interactive and active presentation. So since we got the candy and everyone's kind of working on their carb coma at this point, there will be getting up, running around. There will be Q&A. I'll ask for some audience participation, so hopefully we can keep you guys awake and get you going through the afternoon. So as you can see, the title of this is the 3S method for cluster architecture design. The 3S I'll be getting to in a moment, but first a little bit of history in terms of how we got to this point in Oracle Data Cloud and the journey that got us here. Basically, as you said, we've been using Qubole for about three and a half years. These days we're up to 100 total clusters. They don't all run at the same time, but we run about 50 of them all throughout the workday. We have hundreds of developers and various dev teams working on different projects all throughout the day. We use a variety of Presto, Spark, and Hadoop. We use pretty much every engineering engine and method available within Qubole today. We tend to kind of push the envelope in terms of stress testing features and finding new functionality. As you can see, we do millions of QCUH per month. Last month was a landmark month for us. We actually surpassed the 3 million mark for the first time ever. So in retrospect, thinking back to about 2 years ago, we barely was over 1 million QCUH. So we've actually tripled in the past 2 years in terms of what we do with Qubole on a daily basis. Our challenges is basically where this 3S model was designed. We spent many different iterations building different models and strategies for building clusters. And this presentation is kind of for people that are in the provisioning or infrastructure support role in terms of how do I build something that my engineers can depend on and that won't keep me up at night in terms of support calls and having to come up with ways to fix common problems. These are, in some cases, best practices as well, both for users and for infrastructure admins. It can apply to both audiences, but fundamentally we're all about how to build things here, and that's basically why we have Lego stuff involved later. Those 4 build plates, I wish I had more, but that's all I have. Those will be integral later to kind of putting these methods into play and seeing if you can build your own clusters based on some of the best practices that are presented here today. So again, going to the Oracle Data Cloud model here and how our breakdown is as of last month, actually. We're about 50-50 in terms of Spark and Hadoop, and we have a lot of interest lately with Presto. So the 5% there that's Presto, that's actually popped up in the last 1 to 2 months. Again, going back to about 2 years ago, we were probably 80% Hadoop 1. And now you can see Spark has really started to take over for us. Just in terms of what we do, we're mainly in the business of building audience targeting for different marketing companies. And so big data is our thing. We have to deal with, in some cases, 6 months or 12 months worth of shopper and retail data. So we're talking huge data streams, millions and billions of rows in some cases. And the tables may or may not be optimized. So we need to take a number of different approaches sometimes to fixing a problem and figuring out how we can actually make that data usable for people without them having to run their own stuff for hours and days upon end. Again, going back to the 3 million QCUH number, this is our breakdown. Again, 2 years ago, we hardly had any Spark, and now Spark is almost, three-fifths basically of our processing realm. We're actually moving more away from Hive and Hadoop, and we're starting to explore Presto again. So now it's time to solve the question of what is the 3S model. Basically, there's 3 S words that I'm looking for that would be key to cluster design. Does anybody have an idea of what one of those 3 would be? That's one. Scalability is one of the 3. Anybody else? Not so much speed. Speed is a relative term in Qubel, and actually, what I like to say is we don't guarantee speed because it depends on how many people are using a cluster at a given point in time and what type of things that they're doing. So although speed is important and we want to produce speed, it's not one of the common struggles really that people have. They'll always find a cluster that isn't running and they'll start it up and fix their speed issue that way. So stability is another big one. Okay, yep, stability is number 1. There it is right there. And like you said, scalability is number 2. Basically, if your clusters aren't stable, then people are rerunning things multiple times throughout the day, basically using up excessive costs and not getting much to show for it. Plus, they get very frustrated. Scalability basically helps you keep costs down while providing a robust infrastructure for your engineers and your developers to build on. So I'm looking for one more. Spot is nice, but spot isn't always guaranteed. We like security, but that's like a whole nother talk, so I won't get too much into the secure aspects of it. But yeah, security is always important, and my security team would hang me if I said otherwise. Think practicality. Basically, it's how do we keep the bean counters happy as well as keep the developers happy and giving them enough resources to run all of their jobs. This is probably the number 1 thing that's consumed my time over the past year in terms of I have to answer to the people that get the AWS reports, for example, and the cost reports, and basically justify what each cluster is doing and is it doing it to its best of its ability. So I'd say the most paramount here is number 1, stability, but the hardest one to manage and the one that's a day-to-day challenge is the sensibility aspect. So first we'll cover stability. In order to build resilient and flexible clusters, these are some of the best practices in regards to cluster design. Number 1, set your minimum on-demand nodes to be at least 10% of your total max cluster size. Now the key to remember with minimum and on-demand nodes in Qubel is that those nodes are always launched on demand unless you force them to spot. So remember that the duration of your cluster being up is going to be the amount of hours that you're paying for on-demand nodes. So if your cluster runs for a month straight, you're basically running on-demand nodes for a month straight. So it's very important to know the average timelines of each of your clusters and how many of those nodes are running at any given point in time. And number 2 here is increase the minimum nodes of your cluster for more replication during times of heavy spot loss. This is more of an AWS-centric type issue here, but it can apply to pretty much any cloud model. But generally, whenever we find that node loss is high and that jobs are constantly retrying, it's best to increase your minimum on-demand number of nodes and then reduce those back again if you can after you get past the pain point. The question was, whenever you increase the on-demand nodes, can you do it automatically or do you have to do it manually? Generally, you have to have cluster modification permission, and you can change that value on the fly. But there is a bit of a negotiation period that happens there. And if you're using option number 3 here, which is heterogeneous clusters, that can sometimes get a little bit more unstable. Just because heterogeneous clusters, and I did a talk on this last year, it's basically diversifying your instance profile so that you can use multiple types of instances to equal the same amount of compute or memory requirements. So in that case, you may have a building foundation of, say, 4x instance types, but you're willing to accept either 2x or 8x to help meet that need. And I'll illustrate that more in a future slide. But to answer your question, yes, you can increase that on-demand number, and you can bounce it back again if you have to later. Yep. There's about, I'd say, a third of the options within configuring a cluster are hot pushable, so you can do those in a live configuration, and they'll generally either change accordingly or change back. Number 4 here is when using EBS, use volumes of at least 250 gig in size to get maximum I/O performance. Actually, with AWS, you have multiple types of disks that you can use. In general, the most bang for your buck is ST1. But we found that actually, if you're running ST1 for a long period of time, that you can actually start losing performance over time. So if you do have small storage requirements, you don't need a whole lot, you can get by with just 250 gig of GP2. But ideally, you don't want to go underneath that 250 number because then you're actually losing I/O performance based on how AWS's bursting model works. And lastly, again, it's going back to know how long your clusters are up, and if you can, try to restart them once a day just to keep the master node refreshed and to keep your slave nodes getting recycled as well. If you are running clusters that are running long in some capacity, then there's probably some optimization that can be done there. So number 2 is scalability. Again, it's try and build your clusters around the smallest instances able to run your jobs. And I'll illustrate this again in future slides, but with Hadoop and with Spark, you can kind of approach this in different ways. But ideally, you want to scale up. You don't want to be dependent on falling back to smaller types if you have to, because then you'll end up with clusters running maybe 500 or 1,000 nodes before you know it. So actually, in parallel to that, option 5 here is know your service limits and monitor on-demand instance usage. If you do run into situations where you're using a lot more, say, M4 extra large or M4 extra large than you planned on, if you're only allowed 200 on-demand instances in a region, you can hit that number pretty quick. So another way to help with that is number 2 here, use container packing to consolidate active nodes and release idle ones to save costs. Basically, this means that it's constantly polling the cluster and looking for nodes that are actively doing things. And if it is, it'll swap HDFS blocks from other nodes onto those nodes so that it can release the other ones and basically get the cost back from having to run those additional nodes. A Spark specific example here is to use max executors instead of num executors to share resources efficiently. There are purposes and reasons for using num executors, and that's fine. But especially if you're on a shared platform, using max executors means that it's only going to scale up when it needs to, and then it's going to scale back down whenever it's not as busy. So if, for example, you have significant data skew on a task that you're running, and it ends up having only one executor or something running a reduced step at that point, it can let the other executors go and back into the resource pool, and therefore you're not reserving or holding on to 100 or 200 executors, for example, that you don't need. Again, there's a reference here to EBS, and Kubel also supports EBS auto-scaling in their clusters, which basically means it's like LVM volumes in Linux. Basically, as the HDFS local storage on each node gets full, it can allocate and provision some more and basically loop those volumes together and give you more disk space to use. Basically, you'll find as you run clusters for a longer period of time, you start to run out of disk. And so using this EBS auto-scaling basically keeps you from having to spin up more nodes, which takes longer. And it's easier just to add more disk. Lastly, and this is more of a general best practice thing within dev teams, try to appoint data monitors within your teams to monitor your cluster utilization and kill and rewrite jobs. Basically, you're like a data cop. What we find in a lot of cases, especially with people that are new, some jobs may be ran that end up spawning 50,000 tasks within a cluster, and then they end up consuming all the resources, and then no one else can run anything. So to basically minimize the number of people that have to control that, if you basically appoint some tech leads within your groups that have full authority to basically go and police the health of the cluster, then you can keep things running smoothly. Lastly, we have sensibility. Again, this is basically a cost versus functionality tightrope balancing act. But these points here kind of help keep those things in harmony. Number 1, Kubel has a bunch of different ways that you can submit jobs. The default interface is to use just the query window in the Analyze UI. there is support for a workflow option. The workflow option basically means that you can break your job into each individual stage and use whatever overrides or whatever special features that you need in that part of the job. So say, for example, you need to drop back to MapReduce to do a certain stage, you can do that. Say you need to use TES for a certain stage, you can do that. If you know that you have significant data skew and that you need probably 10 times the amount of memory that you normally would do for that given part of the job, you can increase that value by tenfold in just that part of the workflow, and then once that part is done, it releases it back to the pool again. Secondly, again, talking about memory overrides, it's best to do those within the stages of your jobs rather than at a global job or global cluster level. If you have a 12-hour job that runs from start to finish, if you set those memory parameters to use 10 times the normal amount of memory, then you're using 10 times the amount of memory for 12 hours. Again, if you use the workflow option and maybe that one part that you need that 10 times only runs for an hour, then you're only using 10 times the resources for that 1 hour. Number 3, stages should spawn a sensible number of tasks. 5,000 here is what I recommend, just because that tends to run a good balance, especially in a heavily shared environment. But if you don't have as much contention for resources or not as many people sharing a cluster, or you have an insanely huge cluster, this doesn't matter as much. But that's generally a good number to keep balance of jobs turning around in a timely manner. Going back to before where we talked about minimum cluster nodes being on demand, if you purchase reserved instances for the amount of on-demand nodes that you know you're going to need, that means that you'll always get those at a reduced rate. Again, reserved instances in AWS are for a sustained period of time. So if you know that you're running a certain number of clusters per quarter or something, you can basically review that reserved instance number and make sure you have enough reserved instances for the next quarter. And then finally, down here, I highlight AWS instance types that work well with different types of jobs and different types of clusters. Basically, Spark and Presto are designed to work faster in memory, so you want to target the R instance types, for example, there. For Hive and Hadoop, especially if you're doing a lot of brute force operations or writing out to disk and just processing a large data stream, then maybe CPU is more of what you're concerned with, and therefore the C instance types make more sense. If you do have a case where for some reason you're just spilling to a lot of disk and you can't control it, it's possibly better to look at the I instance types. Those have a lot of fast local NVMe storage. So the odds of you running out is lower, and the network throughput is much higher, so you can get the stuff off a disk back to S3 as fast as possible. And then finally, if either you don't know what you're constrained by, or if you just want to have clusters that are best for ad hoc use, M is your best all-around instance type. It's a balance of CPU and RAM, and it works for many multi-use cases. So now we'll kind of go through each main engine and kind of the heterogeneous and config options that go along best with that. For Presto here, for example, again, you want to use R instance types because those stay mostly within memory. So in this case, we actually set the master and the slave to the same. And these are your base types. You cannot use heterogeneous with Presto. So in this case, you want to set a cluster to a decent size that you know that you're going to get that many nodes of whatever you're asking for. And again, we're using the ST1 disk type here for maximum performance to go along with the speed of the Presto processing engine. Example number 2 is a Hadoop cluster that we have. And you'll see here's where heterogeneous is actually being used. The ratios that you see next to the other types listed here underneath the master and slave, that basically shows the ratios of each of those types that you get in regards to the request from above. So whenever your cluster is set for, in this case, 20 to 200 nodes, initially you're going to run 20 M4 10Xs here. If for some reason you can't get 10Xs, then you can either get a combination of 16Xs at 1.5 to the normal base type there, or 4Xs where you'll get 2.5 for each normal M4 10X that you would use. The 200 maximum slave nodes there is basically based around that M4 10X size. So that would be 200 M4 10Xs or And my math might be a little off here, but I think it would be like 350 for 4x's, and then it would be maybe 150 or so for 16x's. So if you know that you have a lot of resources that you need in terms of number of nodes, sometimes it's better to use the higher instance types if you can, just to keep your total number of nodes down. And these are always based on spot bid pricing at the time. Basically, if you can get 4x for the cheapest, you'll get the 4x's right at this point in this configuration. If the 16x's are actually the cheapest based on going rate, or if there aren't any spot available, then you'll get those 16x's instead. But again, during periods of high spot contention, this allows you more flexibility than normal in terms of you have 3 different instance types you can possibly acquire instead of just being dependent on one. Lastly, we have the Spark example here. Spark is a little bit more unique in terms of it supports notebooks. And we recommend the user notebook interpreter mode because that means the resources for the notebooks runs in the master node. Therefore, we recommend the master node being one instance type higher than you would normally use for the slaves. If you're already using 16x's all across the board, then obviously you can't use anything higher. But this would be kind of the most flexible configuration. And whereas before with Hadoop, we went one instance type larger and one instance type lower, with Spark, you want to keep going higher because odds are your developers and your engineers are building executor sizes based around that base node type there. So if it fits within a 4x, it's going to fit just as well in an 8x or a 16x. Whereas if you had to go down to a 2x, you might run into fractions of executors, and then you have wasted resources. So that's basically the core of the presentation in terms of talking about best practices about cluster design. Basically, this is the point where we would normally move on to the Lego part. But I'm going to go ahead and open up for questions now in case you have questions about building so that we can apply that to the exercise here in a couple moments. No questions? Okay.
Are you guys having to coach your analysts on how to run queries and how to write? Are you guys having to spend a lot of time doing that?
Ideally, I should. We do offer some basic practices, but it's kind of like, again, our model is we have a very small number of people that are actually governing the infrastructure and kind of keeping the lights on, so to speak. But we have hundreds of developers, so it's kind of like a 50-to-1 sort of support model there. So basically what we do is we kind of have a permissive model. We build big for a month. You get a month to impress us with your statistics and your cost numbers, and if they're gaudy and a little suspect, then we come back and try to do a little bit more coaching. Ideally, everybody might not have that sort of budget to play with, but we find that at least internally with our culture at Oracle Data Cloud, a lot of people feel driven and motivated to kind of play and find what works best for them. And we kind of have almost like an internal mentoring sort of program within teams in terms of that new interns or whatever that come in will work closely with like the principal data scientist and figure out the best practice stuff and whatever happens to be unique to that team. And in some cases, some of the recommendations here may not apply to some of the more advanced use cases. So in those cases, we make exceptions. And the question was whether we build large clusters or tend to build smaller clusters. And actually, I would say it depends on how well your developers and your coders know their data sets. And this example will illustrate that whenever we get to the exercise. If you know your job is CPU bound, for example, then it's good to build a CPU specific cluster that they can run their job into because it's going to run more efficiently. But like especially when people are getting a feel for the platform or starting to create a new job, they may not know whether they're CPU or even I/O bound at that point. And giving them a cluster that's big enough to let them basically find their choke points and their struggles allows them to fine-tune that a little bit more, and then you can scale things back later. So it really comes down to your budget and how big your teams are. I'd say if it's a small team of maybe 6 or less, you could probably get by with like a 4x instance type, for example. And for most part, people should be able to operate within that. If you're talking about dev teams of 20 and up, then it's probably more to break those down in terms of projects or specific teams working on specific projects and figuring out, again, where those choke points are and what makes sense to give this group that cluster and that group that cluster.
Oracle makes lots of decisions for cost savings, but they're like large, like data-wide. Like is there like a monthly meeting where people get together and go, I'm looking at A, B, C, D, and E. This is too high, this is low. Like, what are the metrics you guys use to make decisions that affect how you populate your data, especially either from cost or efficiency? I know a lot of it's cost.
Yeah. I basically crunch the numbers for both QCUH and for like EC2 spend in this example. And basically, I want to make sure that the ratios are going up proportionally. If QCUH went up a lot, but EC2 did not, then my question is, what are we doing right in terms of you're processing more with the same? The adverse, though, is more concerning in terms of cost going up, your QCUH is going down. That means that you're not processing as much as you are, but your costs are going through the roof. So at that point, then I'd be looking into whether clusters are deadlocked, whether we have people running processes that are restricting other people from running processes, or if we run into situations where the spot market starts to get more volatile, you may need to move to a different AZ. You may need to look into some other configuration options, like instead of heterogeneous, you can do multi-AZ. AWS, for example, recently has changed their spot model in terms of you can't actually bid a high percentage and hold on to spot nodes. Whenever the market dries up, they just start pulling back. So you need to be more flexible and need to have basically fallback options here in case you can't get what you're normally used to operating with. Okay. So yeah, QCUH, EC2. I look at storage costs these days just because we do have EBS auto-scaling turned on, and if your clusters are up for long periods of time, once you auto-scale up with EBS, you can't scale back. It's an LVM volume, so once you grow it, you can't shrink it back. So if your cluster spun up once 2 weeks ago and it's been up solid straight, well, you've just been running with potentially 1.5 terabytes of disk space, but you only use maybe 200 gig on a daily basis. And
do you have any alerting where you get to see that? Is there any kind of anything running off of Ganglia that you guys have that?
We actually have some stuff built into Splunk that reports on that. And it's basically like on-demand usage. We have, again, the spot percentage that we're getting at a given point in time, which AZs are configured in, and what our usage are in those AZs in terms of our service limits and stuff like that.
Awesome.
Okay, then we'll get to the fun part of the day. Basically, I only have 4 build pads, so you're going to kind of have to group yourselves into teams of 4, or teams around those 4 pads. Basically, how this is going to work, these are your nodes and the modules you get to work with. What's on the table over here? The cards are basically demands from your dev teams in terms of what they need for clusters. Ideally, you're going to have on there what type of cluster they need, whether it's Presto, Hadoop, or Spark, what they're bound on, whether it's CPU, RAM, or in some cases, they're unsure. So you may need to be a little bit more flexible with your build. And then finally, it's going to tell you what resource constraints they have in terms of how much memory they require or how many CPU cores. Again, in a perfect world, these are numbers that you get from your developers. In a more real world, you probably don't know these things off the top of your head, so you just have to kind of guess. Basically, the 2 buckets that we have here, these are on-demand nodes. These you'll use to build for the minimum nodes in your cluster. Again, the 2-piece blocks here are your extra large instances, so your smallest nodes. The 4-piece blocks, the 2x2s, are 2x's, and the 4x2s are 4x's. And in case the colors don't come through very well on the slide here, it's basically white and yellow for spot Cs, different shades of green for on-demand Cs. We have like a pastel blue and a regular royal blue for M4s. And then we have blacks for M4s on demands. And then for spot Rs, we have pink and red. For on-demand Rs, we have orange. And this is only because if you've ever gone to a Lego store and you tried to find certain primary colors and certain shapes all to match, it's a nightmare. I spent an hour in the store, and I almost went crazy. So I forgive the complex pattern here, but again, basically the tubs are your on-demands. The bag is the spot market. When the bag is empty, there's no more spot. So then you have to use on-demand for everything. If you're not on-demand, then you might as well just go home because there's nothing else available for today. So ideally, what we can do to minimize the chaos and confusion, we need to have a couple of people that just kind of stay there and basically are the ones that are good with math in terms of figuring out what builds of these you need to meet the constraints that come on the cards. Probably one runner for each group to come up here and grab a cluster config. I ask that you only come up and run up and get one cluster config at a time, just so that we don't have people, basically barreling over other people to get cluster requests. Ideally, these should come in a nice orderly fashion and let you provision at your own pace. When we run out of cards, we run out of cards. If we run out of time, we run out of time. Any questions about the process? Okay. If you want, we can move the Lego building paths to wherever we want to make them more centric. But kind of group yourselves accordingly and kind of figure out who wants to be the runners, who wants to be the builders, who wants to be the math crunchers, and we'll see how well this works out. And this isn't an exact science. There's no wrong answers. We're not going to keep any of you here after in case you can't build a functional cluster. It's basically just to get practice at this and have some fun. So ideally, you want to build with as much spot as possible, but you do need at least 10% on demand for stability. So I think we got about 2 minutes left. So whatever one you're currently building, that would probably be the last one. Either it's time to dance or we just ran out of time. I don't know. Oops. Oh, no. There you go.
Time's up.
Oh, no. Okay.
Time's up, guys. Let's put down your workloads in the middle here.
Happy hour
Maybe
time.
if you
Everybody
win.
stop building.
All right, so if you put it on the corners where your team was closest to.
So what we got here? Does this go with this one? Yeah. Okay. Oh, okay. So starting with this one here, these guys love on demand apparently, this is good for stability. Might not be good for the people that are balancing the costs at the end of the day. But these clusters will stay up and these will work, and your developers will be very happy with you. Management may not be happy with you. So over here, again, we have on demand, but these are stable and these are good. If for some reason you couldn't get spot, this would still work just as fine. So these are good for Presto, just like these are good for Presto. Man, everybody got the Presto cards. Yeah. No resources or nobody to provision, I guess. So this one didn't happen. This one over here, we have a good mix of spot and on demand for this Hadoop cluster. This is using a 4x and a 1x. Yeah. So this is M. It's good for Hadoop. Again, this is RAM bound, so you could use ours for this, but M is a perfectly acceptable choice as well. Again, for Presto, we're on RAM bound here. The R's were the right choice. Again, this is a pretty big demand, but you have a good balance here. Again, go ahead.
So we win, right?
You do have two clusters done, and they're both a mix of spot and demand, so that is very good. Yes, that's also very good.
So we are the winners, right?
Yes,
Already.
in theory. But these have pastels in the most colored deviation, so this gets the most aesthetically pleasing one. So this is the most robust and dependable one. This is also robust and dependable. This is a good balance of all of the factors that we covered today, and this is also a good balance of everything we covered. But yes, I would give the trophy to that one. if I had to award a winner. Yeah. So hopefully everybody had fun, learned a little bit of something. Obviously, this is not as fun to do in real life, but this is basically what you're doing in a virtual sense. So, thank you.